Okay guys, let's take a look at today's lesson. We are looking at day 2 of Taylor series. So we are the first day. Our goal is to figure out how to do a Taylor series from scratch, either just doing the derivatives like we started out a Taylor polynomial, or using a series that we will have memorized or be given and substitute into the series. So we talked about that. We're going to continue on today. We're going to get a little bit more in depth on Taylor series and discover how we can use them. So this first problem, we're asked to use a power series to approximate this integral. Now let's look at the integral. We couldn't do this integral by hand. We talked about when we first started talking about integrating, we talked about you can't do them all by hand, so that's why we had to come up with ways to approximate. We have a lot of different ways to approximate, right? We could use a Riemann sum. I mean, there's lots of approximation techniques for integration. This particular one is using a power series to approximate. So that's what we're going to do. We're going to use a power series to replace this e to the negative x squared, and then we'll integrate the power series. Power series are just polynomials, so we would integrate a polynomial, and that is, a lot easier than other types of integrations. So that's one of the reasons Taylor series came about, is to help with approximations. Okay, so we're going to work on e to the negative x squared. What I'm going to do is I'm going to actually use e to the x. So see why I'm going to use e to the x and sub into that. So why would I be able to do that? First of all, this is basically being approximated on the integral from 0 to 1. And we know that the series at the center is the most accurate it's going to be, right? If we're centered at 0, it is the most accurate at the center. And so this integral goes from 0 to 1, so it would be a pretty good idea to do the Taylor series at a center of 0. Do I have to? I mean, no. But if I don't, then my approximation isn't going to be as good, right? Because I'm integrating from 0 to 1. So I'm going to, and if I didn't do it at 0, I wouldn't be able to use e to the x, my series that we have already memorized, that one. So let's write down that series, e to the x. So e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus plus then x to the n over n factorial. Okay, so I think this one is probably, of the three that you are required to memorize, this one is probably the easier one, I think. We don't have alternating terms or anything. It's pretty kind of nice. So now what we're going to do is we're going to take this series and we're going to substitute in a negative x squared everywhere there's an x. So everywhere there's an x, I'm going to put a negative x squared in its place. So e to the negative x squared. Here, there's nothing to sub into, it's just a 1. In fact, to make sure we know, how do I know that I can use this series, this known series, to substitute into? Well, my center's at the same place, and my first term is the same. Those are things we need to pay attention to, right? The first term needs to be the same because the series starts out with the first term. If you start out completely different, then, it's not going to work. So here we go. So the first term is the same. So now I'm going to continue to plug in a negative x squared. So this turns into negative x squared plus, then I get x to the 4th over 2 factorial. Then we get minus x to the 6th over 3 factorial plus, I'm just going to do another term. I don't know how many terms I need, so I'm just going to do another one just for fun. X to the 8th over 4 factorial minus ... Okay. I'm not going to write the general term because I'm not going to integrate the general term. I'm just integrating term by term. Now let's see, how do I know how many terms to do? I really don't. We have a requirement that our error needs to be less than 0.01. I don't really know how many terms that's going to be, so I just kind of decided to do 5. If I didn't have the proper, error, I could do more terms, or I could just go back and do more terms. So I just decided to do 5. All right, so now we have our e to the negative x squared. We have it approximated by a Taylor series. Now we're going to integrate that. So from 0 to, integral from 0 to the 1 of e to the negative x squared dx is, okay, so now let's integrate. We're going to integrate this. Integral of 1 is x. The integral of x squared is x cubed over 3. The integral of x to the 4th over 2 factorial is x to the 5th over 5 times 2 factorial. Then we have minus x to the 7th over 7 times 3 factorial, and then plus x to the 9th over 9 times 4 factorial from 0 to 1. Okay. So now let's do our f of b minus f of a. Nicely enough, the 0 is on one of our bounds. That's pretty straightforward to do. So let's start plugging a 1. I get 1, and then I get minus 1/3 plus 1/10. Then I have minus 1 over 42. So I'm going to stop here for just a second. We're finding terms, but we really haven't talked about how to determine what our error is. We really only know 2 types of error so far. The error that we did with the integral, remember that? We did a bound from 0 to the improper integral. And we know alternating series error. So which one of those should we try to use to determine how many terms we need? Alternating series looks like the most promising. We have an alternating series, right? It is alternate. The terms are decreasing in magnitude, right? And the limit of that would be 0. So that's what we're going to think about. And so how do I know how many terms I need if I'm using the alternating series error? Don't I just keep going until I get a number that's smaller than 1 over 100? Right? Isn't that the way it works? And then we stop and chop. You probably remember that, hopefully. Okay, so I'm not there yet. It's just 1 over 42, so I need to keep going. So I go to my next term, and I get 1 over 216. Okay, so here we are. This number is less than 1 over 100, so I'm going to stop and chop. Okay. So my approximation for the integral from 0 to 1 of e to the negative x squared dx, is approximately, and then I'm going to add up these 4 fractions. And you would have a calculator on a problem like this. You wouldn't have to do that by hand. Or you could just leave the fractions, 1 minus 1/3 plus 1/10 minus 1/42. You could do that too. Okay, that's an acceptable answer on the AP test. So I went ahead and added those together just with my calculator, and I got 0.74285. So that's what I would get. Of course, it's a repeating decimal, so that's my approximation. Now, that's great. We've approximated that integral, but we haven't done our finished our work yet. We need to justify and talk about the error. We haven't done any of that yet. So in order to use the error that we just decided to use, we have to say that the series is alternating. Check. The series is decreasing in magnitude. Check. And what was the third thing? The limit is headed to 0. Check. Now, you could say by alternating series error if you wanted to, but you don't have to name it. If you're worried that you're going to forget the name, it's okay, but you do have to put these 3 things. So I'm going to go ahead and say by alternating series error. And now let's set up our error statement. Remember, there are 3 different ways we could write error. Remember those 3 different ways? We could write as absolute value of error, which is kind of my favorite. That's pretty straightforward. We could write it as the absolute value of the sum minus the partial sum, right? That. Or we could write it as absolute value of r, the r to the proper term number. Right, so I'm just going to write error. It seems easier to me. Just absolute value error. So my error is less than, I just determined through this procedure, my error is less than 1 over 216. which is less than what they've required for us to have, which is 1 over 100. And so now I have completed everything they've asked. We've justified our answer. We've shown our error statement. Here's our justification. And here's our approximation. So those are the three things that we were going for on this problem, is to have an approximation, to justify our error statement. Okay? How are we on that? Okay. All right, let's look. We have another example on the second slide, so let's go to that. Okay, that first is a little bit covered up. It just says find. Find a Maclaurin series for f of x equals cosine x. Give the first four non-zero terms in the general term. All right, this is one that we, I'm sure, have already memorized, right? I'm sure we have this down. You know, and if worse comes to worse, we know how to generate it, right? I mean, we know how to generate it. We would do the derivatives, and I mean, it would just take a long time, but you could generate this from scratch. But let's not. Let's go ahead and memorize it. So 1 minus, then we have x squared over 2 factorial plus, then we have x to the 4th over 4 factorial minus, and they want the first four non-zero terms, so I'm almost done. X to the 6th over 6 factorial, and the general term. Okay, so which we would have memorized, or I guess we could write it from scratch if we wanted to. So -1 to the n, x to the 2n over 2n factorial. Okay, that's really all they want us to do on the first part, is just write down. That should be a really easy thing for you to do. This is an excerpt from a question on an AP exam. Okay, so part A, we should get all the points that have to do with part A, so we would already know how to do that. Right, we should have memorized that. Part B, use your answer in A to find the Maclaurin series 4. Now they're telling us to use that series, and sometimes they actually give us a series to use. One that we wouldn't have had to memorize. Sometimes they do that. But this time we created it, and now we want to use it. So we're going to do 1 minus cosine over x squared. That's what they want us to use it for. Now I'm going to generate this. I'm going to sub into, do it all at once instead of in like layers like we did before. I'm just going to do 1 minus this series and divide by x squared, and then we'll have to simplify it. So 1 minus cosine x over x squared is, so I have the 1 minus part, and now I need to copy down this series for cosine, which I just wrote up here. So, and underneath we're going to put an x squared. So then I have 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus. I'm not going to put the general term up here. I am going to need to find the general term because it's asking me to. But what I'm going to do is I'm going to find it from the pattern of the terms that I have left. I'm going to find the general term. I'm going to simplify this out and see what I have left. Then I'm going to write the general term. All right, so let's do that. So I would do, 1 minus 1, so that's gone. Please note that this subtraction distributes to everything inside here. Right, this minus, this is going to distribute to everything, so it's going to change every single sign as we go along. So I'm basically going to have a positive x squared over 2 factorial divided by x squared, x squared over 1. If we flip and fix the complex fraction, I'm hoping we see, as we just do the algebraic simplification, what we should get is 1 over 2 factorial minus x squared over 4 factorial plus x to the 4th over 6 factorial minus x to the 6th over 8 factorial plus dot 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 plus. Okay, so there's the pattern that we're working with. There's a lot of different general terms. We could each write, I don't think there's enough different ones that are people in the room, but I mean we could write a few different ones just depending on where you wanted to start our n at. I'll write down the general term that I used. So I used, let's write it down here, negative 1 to the n plus 1 times x to the 2n minus 2 over 2n factorial. So take a look at my general term and see if you can tell me what n value I started at to create that general term. What n value did I start at? A 1. I started at n of 1. I didn't have to start at n of 1. Here's another general term. I'll just show you, just so you can see some different examples. I could have written the general term this way. Negative 1 to the n x to the 2n over 2n plus 2 factorial. What n value would start that general term? A 0. Right? If I start at n of 0, I'd create those terms. Okay, so we don't have to write the same general term. We just need to be, make sure that it's consistent. No. As long as it means the same thing, we're fine. The only time that it would matter is if they insist that we start at a particular location. And I really haven't seen that, them make us start at n of 0, but it could happen. So we just need to see if they're saying, okay, you have to start at n of 0. I haven't seen them do that, but that would be when it would matter, is if they force us to start at a particular n value. Okay? So now we have completed part B. We've given the first 4 non-zero terms in the general term. Now let's do this last part, part C. Use the answer to B to approximate the value of. Now notice how this, they've just done a little bit of a switch on us. They've changed the variable. Okay, why do they do that? They do that, I think, to confuse people. I don't know, because some students totally freak out. They're like, I am sorry, I cannot change that variable. Really, the variable is just a placeholder, right? It doesn't really matter what the name is. Wouldn't I have the same series for 1 minus cosine t over t squared if I made all those t's as this series with all the x's? I mean, it's just a placeholder, so don't let that bother you. We're just going to change to t's because that's what they're asking us to do. So we're going to integrate from 0 to 1 of 1 minus cosine t over t squared dt, and that's going to be, so we're going to go to here, and we're going to integrate term by term of this series right here with t's in it. So it's going to be 1 over 2 factorial t, and then minus t cubed over 3 times 4 factorial plus t to the 5th over 5 times 6 factorial minus t to the 7th over 7 times 8 factorial plus dot dot dot. Now, I don't really know how many terms I need. I just decided to do 4. I mean, I don't know how many I need. So let's see how we're going to decide. We want the error to be less than 1 over 500. So when it says error, they're not going to tell us which error to use. We need to figure it out. So is this a candidate for the alternating series error? I think that's the easier one. Then we don't have to do another integral. Is this an alternating series? Yeah. Yeah, so why don't we think alternating series error? And I have 4 terms. Maybe that's enough. I don't know. But if it wasn't enough, what would I have to do? Just go back and add another one, right? It wouldn't be a huge deal. So hopefully I have enough. Hopefully. No, perfectly fine. Perfectly fine. Now, we would have to stop it at 3 if we needed 3, but we could have extra ones. Yes. So it depends on the question leader. Normally they would allow the incorrect series to be, you would lose points here, but normally they would allow us to read with that series over here. But it changes every year. I don't know. Normally you would be able to at least get some points down here if you transferred that series. Okay. Alright, so let's go ahead and do our integration. So we're going to put the 1 in. Of course, 0 isn't going to affect anything. Let's see what happens. So we get 1 over, let's see, 2 factorial minus 1 over 3 times 4 factorial plus 1 over 5 times 6 factorial minus 1 over 7 times 8 factorial. Okay, so let's just hold here. Let's see what happens. So, alright, let's look at the numbers that we have. Okay, so what we have going on is we have 1/2. Okay, well, that's definitely is not enough. So we have 3 times 4 factorial. That would be 1 over 72. Okay, we're still not enough, right? We keep going until we come to a term that is less than 1 over 500. The next one we would do is 1 over 5 times 720. Okay. Can we all agree that 5 times 720 is definitely a bigger number than 500? Right? So we would stop and chop. In this case, we only need 2 terms. We only need 2 terms to basically have our approximation be within 1 over 500 of accuracy, because that's what they're asking. Alright, so let's do our 3 parts. So our integral from 0 to 1 of 1 minus cosine t over t squared dt is 1 minus 1/2 minus 1 over 72, which is 35 over 72. So there's our approximation of the integral. Okay, so now let's justify our approximation, why we say it's within the range they asked for. So in order to justify, what do we need to say? That it's alternating. Check. It is decreasing in magnitude. And what else? The limit is going to 0. We could say by alternating series error. Again, if you forget the word, you don't have to put this. I'm going to go ahead by alternating series error. And now let's set up our error statement. So our error statement is going to say error is less than 1 over 5 times 720, which we agree is less than 1 over 500. Right? That qualifies. And so we are done. We have our 3 parts. We have our estimation, we have our justification, and we have our error statement. Okay? Uh-huh.
In your error statement, you put this absolute value bars on the
So if this were a negative, and actually this happens to be not negative, if it were negative, I would include the absolute value bar somewhere to show that that negative went away, because it is absolute value error. Yes, absolute. The error bar, those absolute value bars, that's a safe thing to do. Is just always put them. Anything else? Okay.